Good morning, everyone. I'm going to continue our lesson on the chain rule. I added this graphic that the book had. Just kind of interesting. It shows how one function kind of chains with the other. You see the gears there. And it takes a little while to adjust, but as one function changes, that affects the other one. Okay. And then one more time, a good illustration is on the alternate web page. When you look at this the bottom of the picture here, it shows, I think really well. So you got this composite function, and g of x is embedded inside of f of x. And when you take the derivative of a composite function like that, contrary to what we've been taught in the past, you actually start on the outside and do the derivative of the outside function and then multiply by the derivative of the inside. Like I said, that's just goes against what we've learned about parentheses in the past. Okay, so I think we finished talking about this last time. Yeah, I think this is about where we left off yesterday. So let's go to the next one. So this is something that's hard to see sometimes, and I need all of you to, you got to really concentrate on this, okay? Here we have a repeated application of the chain rule. There's actually two embeddings going on here. The function is, I'll get my pen working here, which is not happening at the moment. Just a second. But as you can see, the function is the sine cubed of 4t. Okay? And the sine cubed of 4t, there's actually three things going on. The outside function is actually, this is like the sine of 4t cubed. So the cubing is the very outermost function. Then as you go in, the next is the sine function. And then when you go in again, it's a 4 times t function. So we actually have two embeddings going on here. So here's the function we're dealing with, the sine cubed of 4t. So first, with our kind of weird, the way we handle parentheses, and how we do this cube thing. This is really, the second line is really what we mean, the sine of 4t cubed. All right, so first we deal with the outer. We do the power rule, 3 multiplied by the sine of 4t, and we lower the power by 1. Now we have a chain rule to do because there's an inner function, sine of 4t, so times the derivative of that. So what's the derivative of the sine of 4t? The cosine of 4t. And we're still not done because inside of that there's an inner function 4 times t. And finally the derivative of that is 4. So two embeddings later, we've got it all listed here, and then we just bring it together. 4 times 3 is 12. And then we just go back to the old notation, the sine squared of 4t, cosine of 4t. So this idea that we can have a repeated application of the chain rule means you kind of have to be vigilant. You have to watch for this, kind of keep your eyes out for it at all times. Okay, so now let me just say we've really, this lesson is loaded. We've basically got 3 new derivatives I'm teaching you in this section. The first one is the chain rule. Rachel, having a little trouble. Glad to have you back. Welcome, Jen. So there are 3 derivatives in this lesson. One is the chain rule. The second is the one we're about to show you, the derivative of natural log. And then the third one is related to the derivative of an exponential function. We're going to take it a little bit further than we did before. So let's get on with the second one here. So the natural logarithm. So when you take the derivative of the natural log of x, it's simply equal to 1 over that thing you're taking the natural log of. And of course, x can't be 0, so we just listed that. All right. So to take the derivative of the natural log, it's 1 over whatever you want to take the natural log of. So let's see an application of that. So in part A up here, we want to take the natural log of 2x. So first, I mean, they don't really show it. What I would do first is say, all right, get my pen here. You've got 1, it's 1 over that thing you wanted to take the natural log of. You wanted to take the natural log of 2x, so that's 1 over 2x. And then we have an inner function, 2x, so we have to multiply by, we got to do the chain rule. The derivative of 2x is 2. So overall, you basically wind up with, you know, when you cancel the 2's, you wind up with 1 over x. So, all right, next one, B, the natural log of x squared plus 1. Okay, put 1 over x squared plus 1. So that would, step 1 would be to write it like this. And then what's the derivative? I'm sorry, x squared plus 1. 1 over that thing you were taking the natural log of. And now what's the derivative of that inner function, the x squared plus 1? Oh, that's a 2x. And then that's your answer. 2x over x squared plus 1. Okay, now in part C, we have a product rule. X times the natural log of x. So here we have to apply the product rule, and we still have to remember how to take the derivative of a natural log. So here, what do we do with the product rule? The first times the derivative of the second plus the second times the derivative of the first. Okay, well, what is the derivative? You know, we x times, and what is the derivative of the natural log of x? It's 1 over x plus the second, and then the derivative of x is 1. So then just simplify it a little bit. So that was just a case of a product rule, and inside the product rule, we had to execute the derivative of a natural logarithm. Part D, we have kind of an enveloped one. We have find the derivative of the natural log of x cubed. So on the so first we got to do the outer function, which is that cube. So we do the power rule. We do 3 times the natural log. We reduce the power by 1. And then because the natural log is embedded in there, the inner function, we have to take times the derivative of the natural log of x, which is 1 over x. Anybody have any questions on these 4 examples? Okay. So I just wanted to show you the proof of the, well, yeah, let's take a look at this. So I wanted to prove to you, we don't usually look at proofs, but I wanted to show you that the natural log of x, when you take its derivative, really is 1 over x. So when you look at the problem, here's the function we wanna basically start with. And what does that mean when y equals the natural log of x? It means the exponent on e that will give you an x. And that's what this says. Y is the exponent on e that will result in x. Okay, so now take this equation I just underlined and let's take the derivative of both sides. On the left side, I'm going to take the derivative of e to the y. Well, because it's an e, it starts with what? Itself. But then y is not x, so we got to do the chain rule. We got to multiply by dy dx. On the right side, the derivative of x is 1. Okay, so now just divide both sides by e to the y. And you now have dy dx equals 1 over e to the y. And e to the y, as we see up above here, is the same as x. So just like we told you, the derivative of a natural log is 1 over that thing you were taking the natural log of. All right. So, all right. Now, we did that already. Did we? Yeah, we just got through with this. Okay. So now, here's kind of a cool thing. Logarithms. Do you remember the properties of logarithms? For example, what's the logarithm of two things being multiplied? It's the log of one plus the log of the other, right? Because if you were multiplying two things with exponents, you would keep the base and add the exponents. So anyway, another logarithm law is when you have something to a power like we do here, you take that power times the natural log of the base, or the log of the base. So in this case, we're going to take this problem, and the square root of x plus 1, of course, can be written like this. It's x plus 1 to the 1/2. And we want to take the natural log of that. And the log power, this is not, I haven't done any derivative yet. The log power, the log of a power says take the power times the log of the base. So this has got nothing to do with derivatives at this point. Now that we are here, now let's take the derivative. We got a constant out in front. All right, let's ignore that. And then what happens when you take the derivative of a natural log? It's 1 over the thing you're taking the natural log of. Yeah, and that's basically it. Just bring the 1/2 back. So remembering your log properties can greatly aid you in taking the derivatives. Here's another example of using log properties to help you out. So we've got on the top this rather complex thing. It's take the natural log of x times x squared plus 1 squared over the square root of 2x cubed minus 1. Okay, well, so first of all, here's the original problem. Now let's use log properties to rewrite this. What happens when you take the natural log of, first of all, a multiplication, x times something? Oh, it's the sum of the natural log of the first thing plus the natural log of the second thing. And when you take the natural log of something to a power, that's 2 times the natural log of the base. And then if you divide, you subtract that. Why is it 1/2? Because this is really 2x cubed minus 1 to the 1/2 power. So this is all done with log laws. I haven't done any calculus there. Now we're about to do calculus. Now we take the derivative of the natural log of x, that's 1 over x, plus 2 times the natural log of something. No, that's just 2 times. What's the natural log of x squared plus 1? 1 over x squared plus 1. Uh-oh, inner function, x squared plus 1, 2x. And that's where that comes from. And then on the last one, 1/2 times the natural log, so it's 1 over 2x cubed minus 1. Derivative of 2x, the inner function, 2x cubed, 6x squared. That's where that numerator comes from. And then basically just reapply, the 2 times 2x is 4x, and the negative 1/2 times 6x cubed is negative 3x. So then it's just algebra. So using log laws, again, can simplify things greatly when you're taking. So, I mean, half of this problem was just using log laws to get ready to use derivatives. Again, I'm going to just take a little pause here. Okay, I do have a question. So how did it become 6x squared? Okay, so what you're doing here, so when you, Michaela, when you take the derivative of this that I just put in the box, the constant you leave alone, that stays out there. Then you take 1 over 2x cubed minus 1, and then the inner function is 2x cubed. And what's the derivative of 2x cubed minus 1? 6x squared. That's where that 6x squared comes from. Anybody else? Sometimes it takes me a few minutes before I catch on to the chat because I've got 2 different screens I have to work with. I have to keep my eye on 2 screens. Yeah, because I can only write on the one. Anyway, it's a long story, but anyone else? Question? All right, I hope I answered Michaela's question. All right, so the next thing I want to do then is so when you take the logarithm to a different base. So up until now we've been doing natural logs, which are base e, log base e. And sometimes you do common logs where you have a base 10. So what this is about is what happens when you have a different base. In this case, they call it base a. And a, of course, could be anything except 1 is silly. So, I mean, what 1 to a power? I mean, that would be like, that's like doing nothing. But any other base, a, here's how you do it. If you take the log to a different base of x, you still need to take the natural log of x, but you also need to take 1 over the natural log of the base. So the natural log of a base a of x is 1 over the natural log of a multiplied by the natural log of x. Let's take an example. Yeah, and this is really not it. Here, let's go down here. It's a little bit out of order. Yeah, I don't know if this is the best one either. Okay. Well, yeah, I guess let's use this D example on this page, please. So we've got y equals, and there you see we have the natural log base 3. I think you can see that. The natural log base 3. So that's like our A. And what they did is they first they used the log laws. All right, if you're going to take the natural log, if you're going to take the log base anything of x square root x, that's like x to the 1/2. Well, that's just take the power 1/2 and multiply by the natural log base 3 of the thing without the thing with of the thing under the square root sign, x. And then because you're dividing, you can subtract the log of the base. So this is not calculus yet. Now comes calculus, way down here on the bottom. So what happens when you take the natural log, the derivative of the natural log base 3? Okay, well, it's the 1/2 stays out there. What's the log base 3 of x? You see right here, it's 1 over the natural log of that base 3. So you see how 1 over and natural log of 3 is on the bottom. And then what's the natural log of x? 1 over x. Okay, minus, and then here we have the natural log of 3 again. So what do we have to do? 1 over the natural log of the base. And then how do you take the natural log of x plus 5? That's 1 over x plus 5. So that natural log 3 that you see in both these fractions on the bottom here, that is, I mean, that's basically what I just taught you. So there's, let me just go back to that law one more time. So when you want to take the natural log of a different base, you're not asked to do that very often. But when you are, you have to multiply by 1 over the natural log of that base. And then go on and just use the normal rules for taking the natural log of whatever it is you're going to do. And that goes 1 over 2. So now here's the third thing. So we've covered the chain rule. We've talked about how to take the natural log of x, and now we've also shown you how to take the natural log of a base, not just the natural log, but the log of a different base. How do you take that derivative? And now comes number 3. And I know you're going to think this is silly because I've already taught this to you. But how do you take the derivative of any exponential function, base a? So here you see the function a to the x. And the answer is, it's itself. Notice it starts off with a to the x itself times the natural log of its base. So here's the new part. Now, you're probably thinking, well, wait a minute. I thought you already told me how to do how to do the derivative of e to the x. But think of it. E to the x is a constant, so that fits. That's an exponential function. What's a derivative? Itself times the natural log of its base. Well, what's the natural log of e? The natural log of e, and what power on e gives you e? And of course, it's 1. So I was right earlier when I told you the derivative of e to the x is e to the x. It is. But really, here's what's going on. You're taking itself times the natural log of its base. So this is like the derivative of e to the x from a little more detailed viewpoint. Okay. I'm just looking back at comments here. Okay. So here's some examples. I mean, I know we've already looked at at D, but now let's look at A, B, and C. Okay. So what's the derivative of 2 to the x? Itself, 2 to the x, times the natural log of its base. Natural log of 2. Okay, what's the derivative of 2 to the 3x? Itself, 2 to the 3x, see it there in the middle, multiplied by the natural log of its base, 2. Here we have 3x is a inner function, so we have to do the chain. So the 3 here is because of the chain rule. So we have the natural log of 2 times 2 to the 3x times 3. And then just bring them all together. All right, let's take a look at part C. So what if we want to take the derivative of the natural log of 10 times the cosine of x? All right, because we're taking the derivative of a log to a different base, we have to divide by the natural log of the base. So you notice that this part right here, the natural log of 10, that's what that is. All right, and then we have to take the derivative of, and then we have to take the derivative of the log of cosine of x, which is 1 over cosine of x. So that's this part right here. So again, that's on the bottom. And then because that's an inner function, what's the derivative of the cosine? Minus the sine. So that's how that appears. So if I was doing it in order, it's all right, because I'm doing the natural log of it to a different base, I have to say, all right, that means I got to put the natural log of 10 on the bottom. And then when I take the derivative of the log of something, I have to put that on the bottom too. Oh, and then cosine of x is the inner function, and what's the derivative of that? Minus the sine. And that's kind of how you would put that together. Of course, then there's a simplification. What is sine over cosine? It's tangent. So you could also write it like this. It's negative 1 over the natural log of 10. You know, you could have just written tangent on the top. Okay. Looking over for questions. So what that brings, so what we did is we're going to take a time out here and we're going to look at all the derivatives we have now learned. And we've put a lot together. I'm not going to go through all the ones in the beginning because we know those. The constant rule, cool, you can ignore the constant. Then we have the power rule. Then we've got the constant multiple rule, all those easy rules on the top. Then the first thing we learned in this lesson yesterday was the chain rule. And the chain rule said, hey, when you've got a composite function, you have to take the derivative of the outside multiplied by the derivative of the inside. All right, and then, well, trig, that was really not new. That was done previously, so that's old again. And then really the 2 and 3 are, the way I number them, the new ones today are those on the bottom. So 2 was, what's the derivative of a constant? Now, what's new maybe doesn't show there so well, but the derivative of an exponential function, I mean, the derivative of e to the x, we've always said is itself. But what it really should have been is what? Itself times the natural log of its base. You know, this is really, get my pen, this is really times the natural log of e. And the natural log of e is 1, so e to the x is correct. But that way you can that handles the one on number 3 here. What's the natural log? What's the derivative of exponential function a to the x? Oh, itself, there it is on the end, multiplied by the natural log of its base. So that, yeah. And then here's the logarithm one. The derivative of the natural log in its simplest form is just 1 over that thing. But what if we change the base? What if instead of the natural log, it's log base a of x? Well, then it's 1 over the natural log of a, and then take the derivative of the base, which is 1 over x. Yeah, so this lesson is loaded. Anyway, that we're not about to do it, but coming up, we're probably going to have a quiz on all of the, all of the derivative rules, and we've got to live with them a little bit first. So that's not going to be next time. Okay, so let's do some problems. So I've picked out some, and some of these are on the assignment. Let's take a look at number 17. There's really nothing unusual here. This is simply what? A quotient rule. Y equals 1 over x minus 2. So you got to go to the quotient rule, denominator times derivative of numerator, 0, minus numerator times derivative of denominator, 1, all over denominator squared. And this one, on top you just get -1. So this one's pretty straightforward. Not a whole lot of comment. It's telling me I'm offline, so you must not be hearing me. Okay, it looks like we got disconnected. It looks like we're back on. So I don't know if you didn't hear me for a second there. All right, so let's do number 23 on the assignment. This is what? A product rule? So let's get at it. You got the first. Pen here. So you got the first. And then you've got times the derivative of the second. What's new here is, you know, you do the power rule, you bring the 4 down as a factor, you reduce the power by 1. You really need to think about the chain rule there, though, right? And the derivative of x minus 2, well, it's just a derivative of 1. So had you forgotten, you'd have gotten away with it there. Okay, plus the second times the derivative of the first. Okay, then it's just a matter of getting everything together. This is 4x squared, you know, and I don't know, bringing it together. Oh yeah, I do want to point out what happened in this line. So here, okay, get my pen working again. So on this line, I need to explain what's going on. What did I do there? So I looked, I have basically 2 terms here. They're underlined, those 2 things that are underlined, 2 things being added. And I want to factor it. Is there anything I can take out of the 4x squared and the 2x? Yeah, I could take out a 2 and an x. So that's why that's out there. Is there anything I can take out for this x minus 2 cubed and x minus 2 to the 4th? Yeah, we could take an x minus 2 cubed out of each of them. And then what's left? If you factor that out of the first term, oh, I got a 2x left, and I have nothing else left. Okay, on the second part, the 2x is not there, but I still have 1x minus 2. Hopefully you can see, all I did was factor on this line. That's called taking out the least powers, because of the 2, x minus 2 cubed and x minus 2 to the 4th, the least power was x minus 2 cubed. And then, of course, what happens in brackets? Well, 2x plus x is 3x. So just simplifying it a little bit. That's a way of simplifying that one. It's called simplifying by factoring out the least powers. Okay. Let's take a look at number 30. Okay. So number 30, we have a ratio, we have a quotient, and it is being squared. So there's no reason not, let's just square it. And that's what I did first there. So on top, t squared squared, it's t to the 4th. Then on the bottom, t cubed plus 2 quantity squared. Now we have a quotient. So therefore we will go back and use the old quotient rule. Denominator times derivative of numerator minus numerator times derivative of denominator. You see how we had to use the chain rule here? That's chain rule, right? Because when you take derivative of denominator, you do the power rule, 2 times t cubed plus 2 to the 1st. And then, the inner function, derivative of t cubed is 3t squared. Anyway, over denominator squared. And then just multiplied some things out and multiplied that out. And then I took out the least powers again out of these 2 terms. I took out, what, between 4t cubed and 6t squared, we can take out, what, a 2 out of the 4 and the 6. We can take a t cubed out of the t cubed and the t to the 6th. And then you notice we have t cubed plus 2, and the lowest power is 1. So I took that out. Yeah, so what's left? On the left, 2 and one copy of t cubed plus 2, because you got to take 1 to the 1st times to the 1st, and that would equal the original squared. On the right, when you take a 2 out of a 6, you get a -3. 2 out of, then you take a t cubed out of a t to the 6, you get t cubed. Well, when you simplify this thing in brackets, that's 2t cubed plus 4, and 2t cubed minus 3t cubed is a -1t cubed. So anyway, I would say, you should get down to either here or here. Either one would be a fully accepted result. Any questions on number 30? All right. Let's take a look at number 50. This one actually isn't very long. How do you take the derivative of the secant of x squared? So I put those blue parentheses in there because they're kind of understood, right? Take the secant of x squared. That doesn't mean the secant times the secant, because had that been that, then we would have written it like this. Then we would have written it as secant squared of x. That's a totally different thing. That's not what's going on. So the secant of x squared means, can you take the secant of x squared? Well, do you remember from the other day when we did all our trig identities, the derivative of the secant is the secant x times the tangent of x? So the derivative of the secant of x squared is the secant of x squared times the tangent of x squared. If you don't remember that, well, you might want to just go back and use the quotient rule. The secant is really what? The reciprocal of the cosine. So write 1 over cosine, do the quotient rule, you'll come up with secant tangent. Okay, now, do you see the chain rule here? Because they're both involving x squared, that's x squared is the inner function. You need to multiply by the derivative of the inner function, which is 2x. Number 60. Okay, cosine squared of 8 theta. So that really means the cosine of what? 8 theta times itself squared. So when you take the derivative, you would first use the power rule. The 2 would come down in front times the base cosine 8 theta. Do we have an inner function? Sure do. What's the derivative of the cosine of 8 theta? I'm sorry, yeah, what's the derivative of the inner? Well, the derivative of the cosine of something is negative the sine of something, 8 theta. Oh, and 8 theta is an inner function too. So you see how we have to use the chain rule twice here? So let me try that again. So the outer function is the exponent. We did that, power rule. Then we have an inner function. The cosine of something is negative the sine of something. And then finally, it's what's the something in the inside? 8 theta. And the derivative of 8 theta is 8. So that's two applications of the chain rule there. And then you can bring it together on the last line. Questions? Let's take a look at number 68. Now, yeah, this one may surprise you how involved this is. Okay, we've got the cosine of the square root of the sine of the tangent of pi x. We've got embedding coming out of our ears here. Okay? So I just rewrote it on the top line. Do you get how I came to this position? I mean, if you're taking the cosine of the square root of this big old thing, that's the square root, that's the cosine of that thing to the 1/2 power, right? Okay. So on the very outside, what's the outermost thing being done? The cosine. So when we take the derivative, we must start with that and say, all right, that's minus the sine of that thing in parentheses to the 1/2 power. And that thing is another power rule. So the next thing we got to do as we move in is we got to do the power rule. You know, that's the power rule is bring the 1/2 down, keep that whole thing in the middle, reduce the power by 1. Now, what's that sine of the tangent? Oh, the derivative of the sine of something is the cosine of something. Oh, look, we got another inner function. What's the derivative of the tangent of pi x? The secant squared of pi x. Oh my goodness, there's another inner, pi x. The derivative is pi. So this is like embedding heaven here. You've got to really kind of stay focused on what's the next thing as you move in. What's the order here? Again, I'm going to pause a little bit, maybe a lot to take in. And there's really no wonderful way to simplify. I mean, you could go back to square root signs, but so that's true. We could do that, but I mean, you can't really simplify it. All right, 68. Let's go to take a look at 72. 72. X squared e to the negative x. Well, it's a product, so we're going to, on the outside, we're going to do basically the product rule. And that's what I'm doing on this line right here. We've got the first times the derivative of the second. Be careful when you take the derivative of e to the negative x, it's first of all itself, e to the negative x, and then do you see there's a chain rule? The derivative of negative x is -1, so that's where that came from. And then, so the first times the derivative of the second plus the second times the derivative of the first. Okay, not too hard to execute. Then just rewrite e to the negative x is e to the x on the bottom. Don't forget that -1 makes the whole first fraction negative. E to the negative x is e to the x on the bottom, 2x on the top. And because they're both the same denominator, we can bring them together over the common denominator. '86. So here we're given a natural log. And remember the derivative of a natural log is 1 over that thing. So what's the derivative of the natural log of 2x cubed plus 3? 1 over 2x squared. I said cubed, but 2x squared plus 3. And because 2x squared plus 3 is the inner function, what's the derivative of 2x squared? 4x. So that's where that 4x comes from. Take a little breath there. Anybody need any time, any questions to come up here? Take a look at 91. So here we have, again, a natural log. But this is the first time we've seen the natural log of a fraction. So how do you take the derivative of a natural log? It's 1 over that thing. Can all of you see that's what this is here? What's 1 over x squared? What's 1 over a fraction just means the reciprocal. So do you see how I just took this fraction and flipped it upside down? Okay. Well, now the chain rule is a big deal. What's the chain rule? I got to take the derivative of this quotient. And so I have to use the quotient rule. So here we go. Denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. The second line, I just tried to simplify this second fraction a little bit. And finally, I'm able, you notice what that allows me to do. This x squared plus 1 here I cannot cancel. Why not? Because of it's part of a subtraction. But this one over here I can. Right? That's a factor. And so that can cancel with one of these two down here on the bottom. That's what I was doing with the slash here. And then you can come to a final result. Okay, any questions? Let's take a look at number 93. We've got a quotient here, don't we? Yeah, one thing over another. And you know the rule for that is the quotient rule. So let's execute. Denominator, t squared, times derivative of numerator. What's a derivative of the natural log of something? 1 over that thing. So denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. And then the rest, I mean, what happens when you simplify this this part right here? It just becomes t. And you can, anyway, you can factor a t out of the top, which I did over here on the right. You see that? I factored a t out there. And then that t can cancel with one of the 4 t's on the bottom. All right, let's look at the last. I have one more example for you. Let's take a look at number 129. So here we have, I think we did that one already. But anyway, the function is, number 129 asks you to find the first and the second derivative. That's what's different. If you look in the book, here, let's take a look. Number 129. Yeah. See how it says finding a second derivative? So in exercise 125 to 132, find the second derivative. So that's the goal. Find the second derivative. Okay, so now we know what's going on here. Of course, before you can find the second derivative, you have to be able to find the first derivative. So that's what I did on this line right here. So the first derivative is, well, the derivative of the sine of something is the cosine of that thing. Cosine x squared. And then the inner function, x squared, chain rule, 2x. Final result, there's my first derivative, 2x cosine of x squared. All right, now find the second derivative. So now I got to find the derivative of this thing over here that I've boxed in. So that's what a product, right? So we have the first times the derivative of the second, chain rule, plus the second times the derivative of the first. Then on this first one, you got 2x on the front and the back. That comes out to 4x squared. The negative came from the sine. And that's really about as far as you can go. So anyway, in number 1, in that section at the end there, you're supposed to find the second derivative. Okay, so again, you can see we had a full day even on the second day. By the way, when I was looking at the videos on our webpage, there's a video for this lesson, 3.4, and it's called Day 3. So, and there's more than one. So you can go there and look at those too. And who knows, maybe by the time we get through, maybe we're going to have a lot of questions and we may wind up spending a third day. I don't know. But there was a lot here. This is loaded. So you already know about the assignment. I just want to point it out again. lesson 3-4. So we've got those 3 odd sections, 7 to 33 odd, 47 to 73 odd, 75 to 103 odd, and then there's some selected problems along with 137 to 151 odd. So it's kind of loaded, and I hope you got a pretty good start on it for today. Did anybody have any questions? Anything you want to go over? Something I went over too quickly? All right, I think I'm hearing silence, so we will call it a day, and I will see you tomorrow morning. Thank you for being there. We have, what, 4 of you left? Thank you.